Let's see, today we're going to start a new chapter. So this is going to be chapter 46. And the topic Euclidean domains. Now, if you think about our study of both f bracket x, right, so polynomials over a field, and our study of the integers, at key moments, we used a division algorithm, right? We proved for both z, yes, of course, has a division algorithm, and then we proved that back in 481, and then in this class in 482, we proved that in f bracket x, the ring of polynomials with coefficients in a field, has a division algorithm. And so at key moments when we wanted to prove something, we use the division algorithm, in particular in showing that each of those was a principal ideal domain, right? We used a division algorithm. So now, so let me say that, right? The existence of a division algorithm was key, or is key, to our study of z and f bracket x. And so, and notice the division algorithm, it showed up, for z. What do we have? Well, we have, that any integer can be expressed as, all right, if you divide a by b, you get this, where the remainder is less than b. And then in f bracket x, right, we said that any polynomial, when divided by another, right, can be written as a quotient, polynomial quotient plus remainder, where now the remainder is satisfied, right? There's always this sort of bound on the remainder. And so in this case, right, it was where the degree, well, it's just not like, so say 0, where the degree of r of x strictly less than the degree of g of x, right? So here, right, we need some sort of measure of a way to measure size. And so if we can somehow get a sense of size in other rings, it's going to turn out that we're going to have, excuse me, we will have a, sorry, if we have a notion of size, right, it will give us, or it may give us, a division algorithm. All right, so that's where we're headed here. And so let's start off with the definition. So let's let D be an integral domain. A function, and I'm going to use the Greek letter nu, so that looks kind of like a V, that's the Greek letter nu. It's going to go from D star to the natural numbers together with 0. All right, this is a Euclidean norm if two things hold. It's also sometimes just called a Euclidean function or a Euclidean measure sometimes, but I tend to use the word norm. Right, so if two properties are satisfied, so number one, for all A and B in D, excuse me, sorry, with B not equal to 0, there exist, what do you think? Call them Q and R in D, such that A is equal to B Q plus R, where right, so remember I wanted to have some notion of size on the remainder. So it'll go like this, where R equals 0, or the norm of R is strictly less than the norm of B. So there's the first property, and then the second property for all non-zero A and B, so let's say for all little a and b in D star, the norm of A is less than or equal to the norm of A times B. All right, so if you have a function that satisfies this property, then we say that we've got a Euclidean norm. Now, and there's a name for integral domains that have a Euclidean norm. We call it a Euclidean domain. So, I guess second definition here, an integral domain that has a Euclidean norm is called a Euclidean domain, which I will usually abbreviate with a capital ED. Okay, so as a first example of Euclidean domain, we've got the integers. So Z is a Euclidean domain. And so the reason, right, I mean, we know that Z has a division algorithm, right? And so let's just put this into the Euclidean norm context, or use the language of Euclidean norms now. So let's say consider the function nu from Z star to 0 union n, defined by nu of A equals absolute value of A. So then, okay, so now we need to check the two properties, but this function here, just taking the absolute value of the integers, turns out to be a Euclidean norm on the integers. So property 1, given A and B in Z, where absolute value, no, not absolute, where B is not equal to 0, we have the division algorithm tells us that A is equal to B Q plus R, where well, okay, what do we know about R? Well, we know that R is greater than or equal to 0 and less than B, strictly less than B. And so, well, R is equal to 0. Or, of course, if R is less than B but still greater than or equal to 0, then its absolute value would be less than B also. All right, so there's property 1. And then for the second property, so second property, absolute value of A is less than or equal to absolute value of A times absolute value of B. Right here, remember, we're assuming that they're non-zero numbers. I should probably write that down to be precise. So if A and b are non-zero, then absolute value of a less than or equal to absolute value of a times absolute value of b, which is equal to absolute value of ab. Okay, so there's our first example. Our second example, well, we know that f bracket x, right, where f is a field, has a Euclidean algorithm. I keep saying that, has a division algorithm. And so f bracket x is a Euclidean domain. What we want to do is now put the same division algorithm into this Euclidean domain, or Euclidean norm context. So in this case, so reason, consider nu from f bracket x star non-zero polynomials to 0 union n, defined by, well, what do you think it's going to be? Right, so remember, this notion of Euclidean norm gives you some sort of way to compare, some sort of measure of size of polynomials, and the obvious thing here, right, is degree. So it's going to be defined by nu of f of x equals the degree of f of x. So then for property 1, well, I mean, f bracket, we don't need to go through the steps. We know f bracket x has a division algorithm that says exactly what it's supposed to say using this notion of degree. And then the second thing, so if we take a couple of non-zero polynomials, f of x times g of x, or f of x and g of x are in f bracket x star, then the degree of f of x times g of x, well, degree can go, sorry, whoops, I don't need to say that. I want to say degree of f of x, right? When you multiply by a non-zero polynomial, the degree might go up, right? So it's less than or equal to the degree of f of x times g of x. Right, so there's two examples of places where we already know we have a division algorithm, right? And now putting it in this Euclidean norm context. Now let's do an example that we haven't seen. So in, yeah, I guess, okay, so in z bracket I star, so remember this is the Gaussian integers, those are the things of the form a plus bi, where a and b are integers. So in z bracket I star, define nu of a plus bi equal to a squared plus b squared. Now, okay, it's not, this takes a little bit of work here to show that this actually satisfies the properties of Euclidean norm. So here we go. For property 1, okay, so let's choose a plus bi and c plus di in z bracket I with c plus di not equal to 0. So now I need to produce a quotient and a remainder. And now, so remember, when you do the division algorithm, what you're doing is you're dividing one into the other. That gives you a quotient and a remainder. Okay? Now, Now what? Okay, so I'm going to look at A plus BI divided by C plus DI. And we know that this can be written as S plus TI for some S and T in the rationals. Right? Right? We actually did that as a homework where we showed that the field of quotients of Z bracket I is Q bracket I. Okay, now this is not going to quite work, right? When I do my division, I need to make sure that the result actually lives in Z bracket I. The quotient is supposed to live in Z bracket I. Right? So here's the trick. So let's let M and N in Z be the closest integers, to S and T respectively. I suppose in the case that it's 1/2, right? If S was 1/2, then whatever. Either you can choose either the one that's bigger or smaller. So what that tells us is what does that mean? It means that S minus M absolute value is less than or equal to 1/2, and T minus N absolute value less than or equal to 1/2. So then, okay, so now this is just sort of rigged to work. So now, it's a little bit messy. So now A plus BI is equal to C plus DI times Q plus R, where, so let's see, Q is going to be M plus NI, and R is a bit of a mess, but it's just rigged to work. So this is going to be square brackets S minus M plus T minus NI times C plus DI. Fine. Okay. So now what do we need to do? Right, we need to check that it actually satisfies the properties. Right. So we need to look at. So we'll say. I don't like starting two sentences in a row with the same word, but it's all right. So now, if we look at nu of R, that's equal to. Let's see. So how do you do it? So remember how complex numbers work. Well, okay, let me just do this. I'm using a property of complex numbers. So it's going to be S minus M squared plus T minus N squared times C squared plus D squared. Yeah, now this is going to be less than or equal to, so let's see, S minus M squared is going to be less than or equal to 1/2 squared. Same thing, this one here is going to be less than or equal to 1/2 squared times C squared plus D squared. And then, of course, this is going to be less than or equal to, or this is, that's equal to, so that's a 1/4, that's a 1/2 C squared plus D squared, which is strictly less than the norm of c, well, let's write it out. So c squared plus d squared, and that is the norm of c plus di. And I was using this property of complex numbers that I'm going to actually haul out here in property 2. So property 2 it's just a property of complex numbers. Is that the modulus of say x y, so the modulus squared of xy is equal to the modulus of x squared times the modulus of y squared. That's exactly what I just did right here, right? Yeah, so I applied the norm, and notice, I mean, I guess I should have said this out loud, right? When we're doing nu of a plus bi, right? That's a squared plus b squared. That's just the modulus squared of a plus bi. Right? It's just complex modulus. So that's why I was able to go from here to here with equality, right? Apply the modulus to this, or modulus squared to each of those. And so nu of x, that's less than or equal to the nu of xy. Oh, sorry. Nu of x times nu of y, which is then equal to nu of xy. All right. Now, I mean, okay, so we have this notion of Euclidean domain. We've got a few examples of Euclidean domains. And then you ask the question, why? Well, what did we do when we were working with both the integers and the polynomials, right? We recognized that, or we used the fact that we had a PID, sorry, I just spaced out there. We used the fact that we had a division algorithm, or in the process of I need to start over. Okay, what did we do when we were working with both of those? To show that it was a PID, we made use of the division algorithm. And so it turns out, anytime if you have a division algorithm, if you have a Euclidean domain, right, you're guaranteed that it's a principal ideal domain. So that's going to be our first theorem. So this is going to be 46.1. If D is a Euclidean domain, then D is a principal ideal domain. Okay, so for the proof, okay, we've got a Euclidean domain, so let's let nu from, well, I don't need to spell it out. Okay, so let's let nu be a Euclidean norm on capital D. Right, that means it's a function from D star to 0 union natural numbers. Okay, so now I need to show that every ideal is principal. So let's keep this sentence going and say, and let capital I be an ideal of D. If it's the trivial ideal, then of course it's principal. So if I equals 0, then I equals the ideal generated by 0, so it's of course principal. Otherwise, Okay, so now let's think about how we did the proof in our previous two settings, right? Who was the generator of an ideal in Z? Well, it was the least positive integer. Who is the ideal in f bracket x? It was any polynomial of least positive degree. Well, I guess I should say non-negative degree, right? So, otherwise, let's let, say, little b in D, no, in I. All right, so we know that we've got a non-zero element, so let's let b in I, where b is not equal to 0. And so how do we want to choose it now? So let's see, we chose a smallest integer, smallest positive integer, and then in f bracket x we chose any polynomial, any non-zero polynomial of smallest degree. So in this setting, so we'll say such that, right? We want to use this minimality, and so we'll say such that nu of b is minimal. All right, so you run through all non-zero elements of I and choose any one of them for which the Euclidean norm is minimal. And why does that exist? Well, just well-ordering principle, right? There will be at least one such b. Okay, so now we need to show that every element in I can be expressed as a product, somebody in D times B. So let's say now, let little a be in capital I. Okay, so now we've got a Euclidean norm. So then there exists Q and R in D, where A is equal to B Q plus R. And either R equals 0 or the norm of R is strictly less than the norm of B. Now, let's look at R. I mean, this proof is basically the same proof that we do for the integers and the same proof that we do for polynomials. So now we're going to notice, let's see, A lives in capital I, B lives in capital I, which means BQ lives in capital I, which means the difference, A minus BQ, lives in capital I. So since R, which is equal to A minus BQ, is an element of capital I, so now what? Well, we've got two options. Norm less than R, norm of R less than the norm of B, or R equals 0. Well, we have a minimality assumption, right? The norm of B is smaller, or the smallest among all non-zero elements, which tells us that this case cannot happen, right? So we have R equals 0 by minimality of the norm of B. So therefore, little a is an element of the ideal generated by B. Yeah. So what? Okay, so that means, okay, so it follows that the ideal generated by A, no, yeah. Wait, what? Oh, it follows that I. What did I do? I chose somebody. Let me just see what I did. Yeah, I chose somebody in I. I showed that it lives in here. So that tells us that the ideal generated by B, or the I is contained in the ideal generated by B. Since little b is an element of I, we have the ideal generated by B. Sorry, I'm feeling a little bit spacey right now. So hopefully you're following this well enough. I needed to get reverse containment also. So therefore, capital I equals the ideal generated by B. Okay, I guess that's a good place to stop. So we'll pick up with this on next time. Okay.